Let's look at a third example of a smart contract, and now at one where not all three arguments are ignored. So that's in module 42 in this week's code folder. And it's again very simple. So the idea is that we want to ignore datum in script context, but not redeemer. And the condition that we check is whether the redeemer is the integer 42, hence the name of the module. So it's very simple if we can easily write this. So we ignore the first argument, the datum, we ignore the third argument, the script context, but this time we don't ignore the redeemer, and we just check whether redeemer equals the integer 42. This here, as you can see, make I for make integer, takes an integer and turns it into built-in data. We can check that in the REPL. If in the REPL I import Plutus TX built-ins, and then I can try out make I 42, and I get built-in data using the I constructor as expected. Okay, so I check whether the redeemer equals 42. In this case, I just return unit without an error. And if the redeemer is anything else, then I produce an error with an error message expected 42. So the rest is as before. I compile it to Plutus core script, and I also have a function to serialize it. In principle, we could write all our validators like this, using this low-level mechanism where the three arguments to the validator are of type built-in data. And that is made possible by the type built-in data, which, as I said, can in principle model arbitrary data, more or less. I keep saying more or less because function types are not supported. And Haskell is famous for treating functions as so-called first-class citizens. So in Haskell, you can pass functions around as argument to functions or return them as results, but there is no constructor that would allow us to encode a function as built-in data. But other data types, those that we would intuitively consider as data and not as something operational like a function, can be encoded in built-in data. In that sense, it's really very similar to JSON, which is also very flexible and can encode more or less arbitrary data. But somehow, especially if you're a Haskell programmer or a programmer used to some other strongly typed language, this feels very wrong because you lump everything together into this one big blob data type called built-in data. So you basically throw away type information. That's exactly one of the big advantages of using a strong type language, that the compiler catches your errors. But if everything has the same type, if everything is built-in data, then the compiler is severely limited in how much it can help you. So what we would like is to give actual proper types to these three arguments, depending, of course, on the case in question, on the business logic of your specific smart contract. So in this case, for example, the first argument we ignore it anyway. So an appropriate type there would be unit. And for the second argument, let's say that we only ever want to use integers for the redeemer. We would rather have integer there. And finally, the third argument is always of type script context. So I can, let's actually type here script context. And finally, this unit, as I also said before, feels very wrong. It would feel much more natural to have a Boolean there. And if we did that, then we could write very simply just R equals 42. So this is what we would like to write. This reflects the business logic much better, and it also feels much more natural to somebody used to strongly typed languages. So we convey much more information in the signature of this validator. from this signature, you can immediately see we don't care about the value of the datum, the redeemer, we expect an integer. And the third argument will always be of type script context. And if it's okay, we return true. If it's not okay, we return false. One small thing I still should change. If you recall, in the original version, we gave an error message, namely 42 expected, in the case that validation failed, that the redeemer was not 42. We can do the same here. There is a function called trace if false from the prelude, and it takes a string and a boolean. So the idea is trace if false will check the boolean. If it's true, the value is just true. But if it's false, the value is false, but there is a debug message given by this string. So I can do the same as I did before. So this is very nice, and this is the code we want to write. Unfortunately, of course, it doesn't compile because we now have the wrong type here. It says it expected something of type built-in data to built-in data to built-in data to unit, but instead we gave it something of type unit to integer to script context to bool. Luckily, there is a function wrap that we defined in the utilities. So I must add that to the imports. I must also add the dollar to the imports. One other thing, I see I now import bool and integer from the Haskell prelude, which is probably okay because I think the versions in the Plutus TX prelude just map to the ones in the Haskell prelude, but nevertheless, because it's used in on-chain code, I think it would make more sense to import that here and remove it here. So we have to look at our implementation of this wrap function next. You find that implementation in module utilities.plutustx. So this is the function in question, wrap. And if we ignore this for a second, it takes a function where the first two arguments are parameterized. So it's polymorphic in the first two arguments. So that will be the type of datum we want to use. This will be the type of redeemer we want to use. In our case, A is unit and B is bool, and the script context, and returns a boolean and turns it into a function built-in data, built-in data, built-in data unit. So maybe it would be easier to understand if we wrote it like this and added these parentheses. They are not necessary. I could leave them out, but maybe this makes it clearer. So the wrap is a function that takes a function of this type and turns it into a function of that type. And how does that work? Well, we are given a function of this type, and we want to get a function of that type. So we want to get a function that takes A of type built-in data and B of type built-in data and context, CTX of type built-in data, and then returns a unit. And if the given function, f here, returns true, it should just return a unit. And if it returns false, it should throw an error. And this is what this check does. So check is from Boolean to unit, and it does have exactly this behavior. So check true will just be unit, check false will throw an error. And in order to apply our given function f, which expects types A, B, and script context and returns a Boolean to these arguments of type built-in data, built-in data, built-in data, we have to convert those built-in datas to A, B, and script context respectively. And we do that with unsafe from built-in data. And this is where these type class constraints come in. So of course, A and B can't be completely arbitrary. There must be a way to convert an A and a B to to built-in data. So I open a REPL for this utilities module, and import where unsafe from data is defined. And let's just have a look at it. So this type class unsafe from data A has a single method, unsafe from built-in data. This is exactly the one we are using here. And unsurprisingly, it goes from built-in data to A. So in type A is an instance of unsafe from data if there is a function to convert built-in data to A. And if we scroll down, we should find the types we are applying this to somewhere here. So we need this for unit, integer, and script context. And they should appear somewhere here in the list. Here's script context. Here's bool. Here's unit. I can demonstrate that in the REPL. For that, I just also have to import Plutus TX built-ins so that I get access to functions like make I or make B. So let's say I want to apply this unsafe from built-in data to make I42. Like this, it wouldn't work because unsafe from built-in data is polymorphic. It takes a built-in data and produces an A, provided A is an instance of unsafe from data. But if I write it like this, there's no way for the compiler to know that I want an integer. So I must somehow specify which A I'm expecting here. And one way to do that is by giving a type annotation like so. And then indeed it works. So unsafe from built-in data does what we expect, and it turns the built-in data I42 into the integer 42. Now let's again activate this extension overloaded strings. If I now did the same for something that uses the B constructor, for example Haskell, then I will get an error message. It can't be converted. The exception here is not an I. So I say I want an integer. So unsafe from built-in data is expecting something with the I constructor, but here I give it something with the B constructor. If, however, I try to convert this into built-in byte string, then it works and I get Haskell back out. So in particular, that means if somebody now tries to spend something locked at this smart contract and provides built-in data of the wrong type, so in our case, not unit for the first argument and not integer for the second, then it will also fail because the conversion from built-in data to unit or integer would fail. So this is much nicer than before. We have this typed version now, which is much prettier and much more type safe. But as I also mentioned before, there is a performance hit. So if we look in the assets folder for the serialized versions, this is the untyped one. And in comparison, this is the typed one. So we see this is quite long. And this one is relatively short. So there's a lot of overhead even in this small example for the conversion from built-in data to unit or integer in our case. Nevertheless, as I mentioned before in this course, we will mostly use this typed version to write validators because I think it's easier to understand them and easier to write them. And as I also mentioned before, there are ways to make this performance impact less severe. So there are tools that can somehow optimize the resulting Plutus core script or use some other tricks to have the type safety on the one hand, but not have to suffer from the performance impact, or at least not so much. So now we have seen how to write typed validators, and we saw that in action for unit, datum type, and integer redeemer type. And we also saw that there are a lot of predefined instances for unsafe from data. So we only used it for unit and bool and script context, but we saw there was a long list. Nevertheless, what you really want is to also use it for custom types. Often, if you have a specific business problem to solve, have a specific smart contract in mind, you have very specific data structures, often in the form of record types, for example. And ideally, you want to use those for datum and redeemer. So normally in Haskell, what you then do is you have to write an instance for the type class in question. And of course, we could do that. So if we have a custom type, we could manually define how to convert built-in data into a value of that type. However, luckily, we don't have to because there is template Haskell support for doing that. So here's a silly example. So recall in the last example, we looked at the redeemer that was of type integer, and validation succeeded if that integer was 42. Now, as a silly example, let's say instead of integer, we use another type. Just in this example, a new type wrapper, my silly redeemer, around an integer. And we want to use this as redeemer, not just integers. So we could, of course, write an instance by hand, but instead we can use another piece of template Haskell magic provided by the Plutus libraries, unstable make is data. There's also a stable version. The difference is that you have more control over how exactly values are deserialized when you use the stable version, but you also have to provide more detail. So for now, it's enough to use this unstable version. So what you have to do is use this unstable make is data, and then the name of the type you want to implement this type class for. And the way that's done in template Haskell is to quote a name, you use two single quotes. So these two single quotes together with my silly redeemer, this is now the name of this type. And this line says, insert in the source code of this line instances for my silly redeemer. And actually, it doesn't only provide instances for unsafe from data, but also for two more type classes. So if we go into the REPL and ask for information on my silly redeemer, then we see it does indeed now have an unsafe from data instance, even though we didn't manually write that. It also has instances for from data and to data. So those two classes we haven't seen before. So let's ask for information. It has a method from built-in data. Recall in the unsafe from data class, there was a method called unsafe from built-in data. So this one has a not unsafe one. And the only difference is that instead of having return type A, it has return type maybe A. So we saw earlier when we tried to use built-in data built with the B constructor, this B Haskell, when we try to convert that into an integer, we just got an error. If we tried the same here, instead of an error, we would get nothing. So actually we can try that. So from built-in data, let's say make I 42, maybe integer. We get just 42. But now if we take the other example that failed earlier, it still fails, but now it doesn't result in error. It just gives us a nothing. So that's a safer way to do a similar thing. Conversion from this data type or built-in data to another Haskell type. And finally, we have this to data. So let's ask for information about that. And as the name suggests, that has the conversion in the other direction, so serialization. An instance of to data can be converted into built-in data. So we can try that as well. To built-in data 42 gives us I42. And if we use Haskell, then we get B Haskell. And this template Haskell, Plutus TX unstable make is data, or the other version, the stable one, implement these three type classes for us. And then we can just use these types after they are instances of, in particular, unsafe from data. We can just use it in a validator. So where earlier we had integer here, now we can use my silly redeemer instead. And it just works. So the compiler sees that this is an instance of unsafe from data. So the wrap at this point works. Recall the wrap had a constraint that the datum and redeemer types must be instances of unsafe from data. And then the rest is as before. So not only can we use lots of common types like integers and lists and pairs, those already have instances predefined. We can also use our own custom data types suited to the problem we are trying to solve and use those as redeemers and datums. In this context, I want to mention one more topic, namely how to use such datums and redeemers in scripts. So in particular in the Cardano CLI. We saw earlier in the example we tried, the gift contract, that we just use the unit datum and unit redeemer. And we just had that prepared already in this unit.json file here. So what do you do with more complicated values? How do you serialize those to JSON? For that, we also have a utility. It's also in this serialize module where we also have this write validator to file. And similar, we have write data to file. So here we see this type class toData again that I just demonstrated. And we can use that to write arbitrary toData values to a JSON file. So for example, if I want to serialize my silly redeemer, I can use this data to file. It's called a file name silly, and my silly redeemer 37. And it created a file there. And it also logs the value to the console. So this is the JSON we would need to serialize this. And of course, I could also try it with something else. For example, I can use a pair consisting of a list of two integers and a Boolean, for example. And I get this pair.json, which is already quite complex if you had to write that by hand. So this utility is also at your disposal. So it's easily possible to convert everything that is an instance of toData into JSON of the right format to represent built-in data or data.